Sorry. I'm not sorry. Yeah, so and Airbus solves this problem by not using a lithium-ion battery. Maybe they didn't have, but they use the nickel metal hydride battery, which is about 70 kilograms more heavy and that's like the one passenger the lifetime of the plane. That's a lot of money. Safety first. Okay. So these are the issues. What happens? Got it. I got it. All right. Yeah, there we go. This is the star of the show, lithium ion. If you haven't heard why it's called lithium ion, because there's no metallic lithium. You have lithium slipping back and forth between these two insertion electrodes, graphite on one side and transition metal oxide on the other. And this is a safety measure because metallic lithium is very hard to handle. Although people are now trying to go back to lithium metal, but making it safe is a real challenge. The lithium ions move within an organic solvent, which has approximately the same energy density as kerosene. Okay, that's the fuel for the fires when you have these events. So I call this electrolyte bottleneck. The electrolyte inside is a mixture of organic carbonates, and that hasn't changed much in 25 years. There are occasional tweaks, but this is basically what we have. And there's the source of lithium is LiPF6. There's a lot of new work on fluorinated carbonates, polyethers. There's even a lot of effort on aqueous electrochemistry. Aqueous batteries, of course, the voltage will be lower, but you can't argue with these safety advantages to get it to work. New salts to replace the LiPF6. A lot of work on ionic liquids, and a lot of work and a lot of hype on solid electrolytes. If we can just make these ions move in a solid matrix, we can eliminate a lot of the safety issues. A lot of work on that. Polymers, PEO, polyethylene oxide. One of the things I like to quip about is that PEO has been great for making PhDs. Right? So there's a lot of work on that. I haven't really seen that. There's a little bit. There's a couple of commercial batteries that use PEO. This is a difficulty. How do you make one? This is a well-known problem with material science. How do you make one material do everything you want it to do? Okay, it's always going to fall short. The sulfides fall short in many areas. The liquids fall short in many areas. So this is really the name of the game. Very challenging. So we do NMR, magnetic resonance, nuclear magnetic resonance. It's a great tool for material science, especially for battery material science, because batteries have a lot of these nuclei that are NMR favorable, like protons, lithium-7, for example, boron-11, phosphorus-31, fluorine-19. And one of the nice features of NMR, it's very sensitive to small changes in local structure. You don't have to have a well-formed crystalline. You can have amorphous disordered materials because NMR measures very short-range interactions on the scale of sub-nanometer, right? It's also quantitative, right? So if you have a spectrum with many peaks, if you integrate the integrated area of each of those peaks is proportional to the number of nuclei in that particular phase. There's also something like 10 orders of dynamic range, depending on which experiment you do. So you can talk about how the ions actually move inside of the material. We use a technique called diffusometry and also relaxometry. So this is how diffusometry works. This looks fancy, but this technique has been around since the 1960s, right? It's gotten better and so forth. But the idea is that you do an NMR experiment. If you have a non-uniform magnetic field, you have a gradient, then each little slice of sample is at a different magnetic field. Okay, so this is how you spatially encode the material. And if you do an experiment to get a spectrum, to get the transient response, which you then Fourier transform to get a spectrum, you apply these gradient pulses. Okay, so what happens is, in the time scale of this NMR experiment, if a nucleus has moved from one region to another, it doesn't contribute to the signal anymore because it's no longer resonant. And what you get is a decay. You get this kind of Gaussian-looking decay, and you fit to this equation. The only fitting parameter here is the self-diffusion coefficient. Everything else is under experimental control. So it's the best way to get diffusion if you have a good NMR nucleus. So the other thing we do is when you excite the transition, eventually the nucleus relaxes back to thermal equilibrium. That's called the T1 process, spin lattice relaxation. That also gives you, it's the local fluctuations in the field that actually cause the nucleus to relax. So you're using the nucleus as a really good probe of its immediate surroundings. So in terms of dynamic range, At the slower, like things that related to ionic conductivity and diffusion, we have these 2D exchange experiments. T1, which I just talked about, has a range of validity. And it is a technique that we use, which is fairly uncommon in the US, more common in Europe, is fast field cycling elixometry, where basically we polarize the nuclei and we ramp the field down very rapidly. And it takes an expensive instrument to do that, like 2 or 3 milliseconds. And we let the nucleus relax in the lower field, and then we ramp up to the depth. So most of the relaxation occurs in low field, and we can change the value of this relaxation field by 4 or 5 decades of frequency. So we can map out really, over a very broad frequency range, we can map out the relaxation behavior. So polymer electrolytes is an area that I've been involved in for many years. There are major advantages. You can use the know-how of the plastics industry to make very large sheets. And also they're kind of soft, so you get very good cohesion with the adhesion between the electrodes and the electrolyte. Because the battery is basically going to breathe when you charge and discharge. If you have a rigid ceramic solid electrolyte, you're going to break that contact after a few cycles. So that's another advantage. Disadvantage, it's really hard to make one with sufficiently high ionic conductivity. A lot of people are working on that. And there's also, it turns out that the anions tend to be more mobile than the cations in lithium. Okay, that's also a limitation. So if you can make one, this is work that I did for a company in Boston area. You can actually adjust the chemistry. In a regular lithium ion battery, you have the same liquid electrolyte that soaks through both electrodes and then some separator in between. But if you could electrochemically tailor a material to be more stable against the anode and the cathode, you can, by tweaking the composition or whatever, then you can have an optimized electrolyte in proximity to the cathode. Same for the anode. And you have a third composition, which allows the ions to go back and forth between the two of them. So this is a way to ionically wire. If you take apart a lithium ion battery, the electrodes are going to have carbon black in them because you have to get the electrons in and out. But you also have to get the ions in and out. And this is how you kind of ionically wire them. All right, first project. Tracer batteries, cellulose. This is a collaboration with the ARPA-E program at the University of Maryland. And so this is kind of one of our claims to fame. There's 22 authors of this paper because we hit it from a lot of different angles. The basic, this is a collaboration. Again, it's Maryland is where the hub is, and several universities, including our own, working on various different aspects of this. So the idea, again, you want to be on this perimeter if you can. And this copper activated carbon cellulose nanofiber, the conductivity is up here where you want to be. And the basic idea is fairly complicated. So copper basically opens up these channels into which one-dimensional channels into which lithium ions can move. And the ions themselves are also they're interacting with functional groups in the cellulose. They're also interacting with residual solvents, like carbonates, a little bit of carbonates, even water. Okay, so there's about 10 to 15% solvent, but that solvent is very stably bound. It's not dripping wet. It's not a bone dry electrolyte, but it's not dripping wet either. So we get high conductivity, high lithium transference, which I'll summarize in a moment. And you also make pretty flexible, strong films. If you use it as a separator, right, to between the electrodes, you can also use it to ionically wire the electrode particles. So, for example, for lithium iron phosphate, which is a very popular kind of battery, lithium battery, if you look at the overpotentials, meaning you've got excess polarization over here without ionically wiring the cathode particles. When you do that, you get a very small overpotential. So this really shows that it works, that you're much better able to get the ions in and out. And that's very, very crucial for charging rates. So how do you make the stuff? First of all, you have to get the copper in. And the way they do it, my colleagues, is to soak it in a copper sodium hydroxide solution. And then it takes a couple of days to do that. And when stuff turns blue, then you've got copper in there. And then they actually, they dry it off, and then it's soaked in a standard lithium electrolyte type of solution. And you get some ion exchange between the sodiums and lithiums, and you also incorporate some of the anions, the TFSI. So what we do with NMR is, we know that NMR is quantitative, reliably quantitative, although the actual measurements are fairly painstaking. It's good to have a very patient postdoc or grad students doing those measurements. And so we use NMR to estimate the concentration of sodium and also the other solvents, such as water. So this is kind of a roadmap for what we do to estimate by quantitative NMR the concentrations of these various things. We also look at at the molecular level, what's the structure of this stuff by solid state NMR. So we measure diffusivity by this pulse field gradient. We also do magic angle swinging because these materials are really more solid than they are anything else. To get high resolution NMR spectra, we have to spin. We have some good nuclei to play with. We have, of course, proton NMR, fluorine-19, carbon-13, lithium-7, and also sodium-23. Challenge is that copper-2+ is strongly paramagnetic. And even though it does what you want it to do inside the material, it kind of messes up the NMR if you have too much copper in there, because it broadens the NMR signals because the electrons spin on the copper. I actually tried to convince my colleagues, why don't you use zinc, calcium, right? Because you make my life easier. They actually did that, but the stuff doesn't work. Okay, so you can't. I spent too many time. I've had too many examples of me trying to drive the science by just my own personal convenience, and that's not a good way. Not a good way to make friends. So here's a proton NMR spectrum. We can resolve the big broad peak is the cellulose, basically the cellulose host structure. We can also see the residual solvent, and we can integrate these peaks to get the amounts, right? Because again, using the quantitative nature of NMR. And these peaks over here, they look fairly narrow, but they're much broader than they are in a pure solvent, which means that they are confined inside the cellulose. They're not that mobile. So we can actually assign these peaks. We don't find any free. If we had free solvent, we get a much narrower spike over here. So we can actually, when you tell a lithium battery person or company that you've got water in there, they usually slam the door on you. They don't want to hear about it, but the water apparently is a small amount and stably bound inside the material. It's not bone dry, but we also have evidence that the residual solvent also assists with transport of the lithium ions itself. Oops. Okay, sorry, quick thumb. So the spectrum are fairly boring. There's a very narrow line, which implies that lithium ions are moving fairly rapidly. Same thing for the counter ion using fluorine-19. We conclude that even though the way the lithium gets in may be two different ways. Some of it comes in with its counter ion, and some of it is actually ion exchange with the sodium. But all those lithiums are contributing to the conductivity. We only get a single peak. So here's the hard part. For me, easy, right? I just get to go to places and give talks, right? But my Monisha Garaga, my postdoc, former postdoc, actually to quantitate this, you use a standard, right? So you take a known amount of material and you weigh it, and you get the NMR spectrum, and you integrate the intensity, and you usually do a series of these, or a couple of these, and from that you can back out the lithium concentration in the sample that you want to measure. Okay, so it's straightforward in principle, but in practice it's fairly painstaking. So we get the lithium concentration this way. We do the same thing for fluorine. The fluorine spectra are fairly broad, so we actually had better luck by looking at solutions of LiTFSI and to get the intensity, the known amount of LiTFSI. So we have this calibration curve for our standards, and then we can back out the fluorine, the LiTFSI concentration in the actual membrane, polymer electrolyte. So we find actually that the lithium is almost 3 to 1, a little more than 3 to 1 compared to the TFSI, which means that 2/3 of the lithium got in there by ion exchange with sodium. Okay, so how do we prove that? Well, by looking at sodium and more. This is actually a different sample, but the same idea. We take a We take a membrane before we put it in lithium electrolyte, before we ion exchange it, and we measure the sodium-23 spectrum. Then we do it afterwards, and we find that the sodium signal intensity decreases to about 20% of its initial value. So this is kind of our fairly convincing proof that the lithium is ion exchange with the sodium. So that's the quantitative NMR. For diffusion, we get these curves, from which we can extract the self-diffusion coefficient. Remember that the D value is the only fitting parameter when you fit this data. And we get the diffusion. Notice that the lithium is diffusing faster than the TFSI. Anybody who's done polymer electrolytes like PEO, that's the other way around. The ions are much better, are more mobile. The anions are more mobile than most polymer electrolytes. Here, the lithium is more mobile. And because with that, coupled with the fact that you have 3 times as much lithium as you have TFSI, gives us what's called a very high transference number. The transference number is a fraction of current carried by the lithium ions. You want that to be as close as 1 to possible. Okay, you want only lithium to be moving back and forth. Otherwise, you get, if the other ions can move, you get polarization effects at the other electrode. So this is a very desirable outcome, something that's fairly close to 1. We also have evidence, which I don't have enough time to show, that the conductivity is actually anisotropic. It actually moves better along the fiber direction than perpendicular. So near-term challenges, we'd like to get them down. I was talking to Ryan the other day about how goal-oriented these agencies are. So mileposts, this kind of thing. So they want us to get down to 60 microns. We want a better understanding of residual solvents and so forth. And we'd like to go to a higher voltage electrode like NMC, nickel manganese cobalt. LFP is only about 3.2 volts. NMC is 4.5. And we're looking at ways to try to address these diffusion. And so, but here's the goal. This is what we want to be able to do in another year. We want to make a lithium metal battery that you can charge in 50 minutes. Okay, that's a little bit ambitious, but that's kind of what we thought that we're going to try to do. All right, let's switch topics. The second topic, large scale storage. Okay, renewable but intermittent energy. These are the kind of candidates we have right now. Pumped hydro, you just pump water up a hill and then let it run down the hill through your turbine when you need the energy. Huge flywheels. The lithium ion industry wants you to use lithium ion batteries, okay? And I don't think that's going to be the long-term solution. There is a lot of talk about using repurposed batteries, like after electric car has gone, 8 years, whatever, and the battery's capacity going to 60%. You might be able to repurpose them for grid storage. That's an idea that's out there. In my very humble opinion, I think sodium is going to be a much better choice because of its supply, okay, compared to lithium. And then of course there's redox flow batteries. Okay, so this is the some slides from a course by my colleague at Case Western, Jesse Wainwright. The old reason for grid storage was to improve efficiency, robustness, congestion relief. The main reason now that everybody wants is we need to be able to enable energy from intermittent sources, renewable sources, solar and wind. Okay, and also peak shaving. Flow batteries have a very good record, and in terms of these characteristics, long duration, inherent safety. Right, these are not little tiny things that you need to squeeze into your laptop. Right, these are huge tanks. But for grid storage, you don't care about the footprint very much. So they're not energy dense. But you can also independently size the power and energy requirements, and they're scalable. So what do I mean by that? Is this is California, right? You can have nasty weather in California, right? And so these are the 24-hour cycles, solar cycles, and then you have days of terrible weather. What are you going to do? I mean, you could also fire up your coal plant or your natural gas plant. But if you have a really big flow battery, you can provide electricity. You can, really kind of have the constant load that you need. So for multi-day storage, flow batteries are really very leading candidates. By the way, this is from an old slide from my friend Nate Lewis at Caltech. if we had to supply all of our primary energy, everything, transportation, home, electricity, everything, we need about 3 terawatts. This is what a 3 terawatt square looks like at 10% conversion efficiency from sunlight to electricity. It's doable. I mean, look, you guys take it on the chin because we're in Arizona. But of course, it would be distributed, you know, but this is an easy way to show that if we really had to do it, we actually could do it, right? Okay, so flow batteries. The basic idea is you have this redox chemistry. The most common kind and successfully developed is the vanadium redox flow battery, where you have, in one side, you have vanadium mixture of 4+ and 5+, and this side you have 3+ and 2+. And the electrochemical reactions occur at the electrodes when these two things meet. You get electricity out. And of course, these are reversible. You can recharge these electrolytes. So in a lithium ion battery that's sealed up, the energy is stored in the electrodes. The flow battery, the energy is stored in electrolytes, in these big tanks, right? So, the decoupling of energy and power is such that you can have as large tanks as you want to increase energy capacity. For power, you change the size of the electrodes where the reactions occur. So again, the vanadium redox flow battery is in commercial use right now, but you know, maybe not able to develop them for large scale deployment in the country because of expense and mostly because of expense. So, for example, for a home flow battery, you'd need a tank that's about a couple of tanks, 600 liters each, 20 inches diameter by 5 feet tall. For 1,000 homes, which would be a typical home would be about 24 mega for 1,000 homes, 24 megawatt hours per day. You need 2 tanks, and this would be the kind of size. This is compared to a 1 megawatt wind turbine. These would be your tanks about 600,000 liters each. So this is doable, right? We can put them right next to the wind generator. Okay, so our interest is in developing sustainable electrolytes for flow batteries. Okay, so we're working with class of materials, class of solvents called deep detected solvents, which I'll define in a moment. Of course, you need to add your electrochemical redox couples in there, which I won't talk about because that's not really not an area that we work in. We're mostly interested in solvents, and this is part of a large collaboration between Case Western is the hub, and we have this a big effort at the University of Tennessee, Knoxville, NYU, Columbia. Well, Columbia is actually not involved anymore. Notre Dame and Brookhaven National Lab. So we're interested in looking at these deep detected solvents. What is a deep detected solvent? What is a eutectic in the first place? It's basically you want to observe a significant depression melting point when we add 2 substances together. Okay, so that's the basic definition. But these deep detected solvents have properties that are very similar to ionic liquids. Okay, a lot of work on ionic liquids, but ionic liquids are expensive. And so there are a lot of advantages here. Thermal stability, non-volatility, non-flammability, electrochemical stability, pretty high ionic conductivity, and they're really relatively easy to prepare and relatively cheap. Okay, so that's why we were funded for, this is now our 6th year of this Energy Frontier Research Center. So as an example of an early candidate is a mixture of glycerol and choline chloride. And so that has really nice eutectic behavior. So basically what you do is you mix a hydrogen bond donor, such as glycerol, with a hydrogen bond acceptor, such as choline chloride. Another hydrogen bond donor you can use is ethylene glycol. The one with glycerol is called glycerine, right? The other one is called ethylene. So the conductivities are reasonably high, compared to an ionic liquid. And then again, to make this actually work in a flow battery, you need to add these redox active agents like biologen, ferrocene, and so forth. Stuff that I actually never learned about in college. That's another story. So I already told you about, this is just kind of a very quick review. I told you about the methods we use, pulse field gradient, to give us the diffusion coefficients. Again, plugging into this equation and getting out the diffusion coefficients. And the fast field cycling, where we polarize the material, ramp it down very rapidly, then repolar, then we bring it up to detect. This is where our probing pulse over here, and we get it. We assume that most of the relaxation has occurred at this low field, and this low field can be varied over 4 or 5 decades of frequency. So that's how we get, again, as I said before, just reviewing, that's how we get a very broad range of relaxation times versus frequency. So this is our T1 that we measure. We typically, when we plot these so-called dispersion curves, we usually plot the reciprocal of T1. It's for the relaxation rate, right, as opposed to relaxation time. And we know what the magnetic field is, and we can translate directly to what the frequency is because of the relationship between frequency and magnetic field and NMR. So this is how we get our frequency-dependent relaxations. And there are many models. This field is well over two decades old, and there are a lot of successful models that can pull out from the relaxation behavior the translation diffusion and also molecular rotations. We have an independent way to measure diffusion by pulse field gradient, but we actually use that to give confidence to our other fitting. So this is what we use. I already showed a picture of that. There's a company in Northern Italy that makes this instrument. We are one of about half dozen in the US that have this instrument. The work I'm showing is based on a fairly recent publication with my colleagues here. A simple 1D proton NMR spectrum. We can identify all these sites. These are fairly well-known chemical shifts. This is a standard commercial 400 megahertz NMR instrument. And because these spectra are so narrow and well resolved, we can also measure the diffusion coefficient of each peak. Right? So we can separately measure the glycerol and the choline chloride. So when we do that, we find that as you add the choline chloride, the diffusion gets faster. So what we're really doing is, let me just give you the conclusion first, is that the choline chloride is breaking up the hydrogen bonding network inside the glycerol. So everything moves a little better. We can measure separately the diffusion of the glycerol and the diffusion of the choline. We can't do chlorine. Chlorine NMR, you can do chlorine NMR, but you can't measure diffusion because it has a very large particle volume and the relaxation times are way too fast. Here, this is a pretty good measure of what we're trying to prove. If you take the ratio of the glycerol diffusion and the choline diffusion, first of all, the glycerol is faster, and the ratio actually goes up as you increase the choline chloride concentration all the way to the eutectic, which is about 32%. And so this is kind of fairly convincing evidence that you're breaking up this hydrogen bonding network by adding the choline chloride. So these are the dispersion curves we get according to various models that have been out there, some that we've tweaked a little bit. You can break your dispersion curve into contributions from diffusion and rotation separately, like molecular rotation. And we can actually pull a self-diffusion coefficient out of this. And what we do is we actually compare that to what we get from the direct method of pulse field gradients. And if they're right on, then we have confidence in the rest of the fitting curves. Because we essentially use the pulse field gradient measurement to give us confidence in fitting of this curve. You did a little bit of this before you graduated, right? Okay. The problem is the fast field cycling is a very low resolution NMR technique. You see all the protons. Okay, so if you actually have a mixture of two different materials, then you're going to see all the protons. You're going to get an average behavior. So if you can, it's better to deuterate one compound, one of the two separately. To deuterate these separately. That way, you know exactly what you're looking at. At the time we published this, deuterated choline chloride was not available. Okay, but it is now. But we know that up to 10%, the majority of the protons we see are from the glycerol. So we can safely conclude, reasonably, that we're only looking at the glycerol concentration, right? For the choline, we start with deuterated glycerol. Okay, now, of course, there are going to be some protons sneaking in through labile exchange, right? But most of the protons are associated here with the choline. So we're reliably looking at the dynamics of the choline when we use deuterated glycerol. Okay, so at all concentrations. So and here's the kicker here, that using our methods, we can actually get the molecular correlation times for rotation. Right? And we see that as you increase the choline concentration, the rotation time goes down. You're speeding up the motion. You're speeding up the dynamics, not just for translation diffusion, but also for molecular rotation. So we have this both for the choline and for the glycerol as well. So the choline has a longer relaxation time, and it isn't just because of the size. This isn't just because of size effects, but the choline, remember, that is charged, right? So that also slows it down. So here's kind of our summary. We start adding choline. We kind of have these. We still have these kind of like icebergs of glycerol, and we're gradually breaking up until the eutectic concentration always really kind of disrupted the hydrogen bond network completely. So that's our summary for this material. That kind of wraps it up for the technical part of the talk. Just to summarize, novel cellulose-based batteries show a lot of promise, we think, for both a separator and a catholyte, stuff that you use to mix with the cathode to ionically wire into the rest of the battery. We looked at the fundamental nature of transport. We measured the lithium and TFSI transport, and we also were able to quantitatively measure the amount of bound solvent in the material. Nicely, we find that the lithium transfer number tends to be very high. As close to one as you could hopefully get in a material that has counterions, that has anions in it. So again, we want to reduce thickness. We want to go to a higher voltage cathode. We want to better understand the residual solvent, and we want to make a battery that you can charge in 15 minutes. I don't know if we're going to get there. Okay, we're certainly going to spend the money, but I don't know if we're going to be there. Deep eutectic solvents being developed for sustainable electrolytes, redox flow batteries. We showed that NMR can give us valuable information on the dynamics of both the H-bond donor, the acceptor, and the effect on the overall H-bonded network. Again, the translation of rotational motions of all species become faster when you break up that network by adding more choline chloride. So that's it for the technical part. And again, I wanted to take advantage of my relationship with Professor Montano and Saris to say a few words about mentoring experiences. By the way, you can, if you're a faculty member at any university, you can get a guidebook for mentoring. And most of what's in the guidebook is, duh. I mean, the most important thing is you have to be proud. You've got to realize that what you're doing is changing somebody's life for the better, and multiply by the number of students. All right. So I want to talk about some personal success stories, what I've learned along the way. Now there's new wrinkles. I mean, there's certain things you should avoid saying. There's all these like trigger warnings, and there's a whole language about that. I think that's noise, in my humble opinion. Okay, nobody wants to offend anybody, and of course we have to be cognizant of that. But in my experience, all of my students appreciate what I'm trying to do, even if I misstep and I said something wrong. Okay, so it happens once in a while. Did I ever? Anyway, so it ain't rocket science. You have to want to do this stuff to do it well. That's it, right? So I just give you a little summary. One of the reasons I could talk about this, I've been around a long time. So Arlie Petters was my first African-American student in this. We had this minority access research program. He's a provost at NYU Dubai, but he was a distinguished faculty member at Duke for many years in 3 departments, right? What did I do for him? Mostly just got out of his way, okay? He was, I could see he was a, rising star, very rapidly rising. Jillian Reynolds, the 3rd African-American woman in the history of MIT, did a PhD in physics. She worked for Millie Dressel House, by the way. And she's a scientist at DuPont, Armando Howard, very brilliant student, flunked out of Caltech, and came and stayed out of work for 7 years. He was in my intermediate mechanics course. I remember looking at the midterm and going, who is this guy? All right, and he got his PhD in astrophysics in Princeton. Sandra Brown, 6th African-American woman to get a PhD from MIT in physics, out of a historical total of like 11. Okay, so Dale McLaughlin, he unfortunately did not get tenure at Queens College. Rich Tavares basically followed her husband around because he was like a petroleum engineer, and she ended up teaching high school astronomy. But she had, she could have been a faculty member almost anywhere. Richner is a principal now at Frederick Douglass Academy. Jason Herrera, a very interesting case. He was one of my most promising students, and he just decided he didn't want to do it. Last I heard from him, he was teaching 8th grade algebra in the Bronx. Okay, to me, that says a lot. I mean, I think that he could have a greater effect on his kids' trajectories than I did. Okay, so these things come in all shapes and sizes. Sophia Suarez, remember Sophia? Right, so she's she actually was an undergraduate for me. She stayed in my group for PhD, and she's now a full professor at Brooklyn College, one of our sister campuses. Fatima Johnson, first African-American woman to get a PhD in material science from Berkeley. Chief Diversity and Ethics Officer at the American Physical Society. She just left and she started her own company on I don't know if this is a good time to be a consultant for DEI in most parts of the country, but that's what she's doing now. Emily, I kind of lost track of. She's got a PhD in public health. Jaime, did you meet Jaime? I don't know. Yeah, so Jaime got treated very badly in the applied physics program at Columbia. And they basically booted him out after a year, but they gave him a master's. Came back to my research group, got a PhD, did a postdoc at Brookhaven. He became a chief scientist for a company that commercializes developments at DOE Labs. And he now's in the UK because he always wanted to do fusion. Always, even when, so that's what he's doing now. Jason Van Slykeman is a energy engineer at Hunter Aerospace. Luz Sanchez, did a postdoc at Army Research Lab, and now is the men's designer for a startup company. Amy was not treated well at the University of North Carolina, so she left with a master's. She got an NSF fellowship. UNC did not treat her well. I could be sued for saying stuff like that. I don't care. What did I do? But she's got very happy. She designs tests for the College Board. Lena Gonzalez went to Carnegie Mellon for robotics and bioengineering. She was one of these super 5-year postdocs at MIT, and now she runs a company that she started in Massachusetts. Fernando Vilfuerte. Did you know Fernando? Yeah. So anyway, he went to Caltech for his PhD. Got his he's back in New York working for the New York State Energy Research and Development Authority. Jessica Johnson's about to finish at Rutgers. Ariane, you know Ariane, right? She's about a year away or so from her PhD at Columbia Mechanical Engineering. More than half of my undergraduate researchers who go to graduate school don't go in physics. Maybe 40%. Most of them go in some areas of engineering where they're better appreciated. What can I tell you? Oh, it's this guy over here. All right, Jeremy did actually a summer program here. He's a first-year student at Yale, and Maribel is a first-year student at Rutgers in material science. I've got several in the pipeline right now. And maybe in a couple of years, when I give this talk again, I'll have stories about them. I'm pretty sure I will. PhD students have all done fairly well. Okay, some I've lost touch with, like George Bennett, but most of them are gainfully employed and doing well. Postdocs, Cherno, very interesting. I think there are probably fewer than 5 or 6 beamline scientists at the national labs, and he's one of them. He's African American. Okay, Cherno. Phil Stallworth. Phil is the backbone of my research group. He spent 2 years with me as a postdoc. And then he was recruited by the U.S. Naval Academy for a faculty position. And he left after, he would easily have gotten tenure. But after 6 years, he left. He experienced some racism, shall we say. Okay, so he was kind of unemployed for like, well, he had partial employment for like a year or two, and then I brought him back to my lab. And I convinced the vice chancellor of research at the university to create a position for him, like a researcher, senior research associate. And she did at City College, which is one of our sister campuses. And they didn't treat him nicely. So our vice chancellor actually transferred him to Hunter College. And every professor's dream is to have somebody working for them that somebody else pays. Okay, right? And the SARS can tell you that Phil is there to fix anything that needs to be fixed. The two most commonly heard words in my lab are, "Where's Phil?" All right, so that's Phil. What does it take to be an effective mentor, especially when you're dealing with, say, I don't know if even this term is allowed to underrepresented minority students. Okay, can I just say that? And what does it take? Well, first of all, you've got to be, you can't be phony about it. You got to be competent. You don't have to be a Nobel Prize winner, but you have to be competent and passionate. You have to know what you're doing. And if students, you need a certain degree of credibility for students to entrust their future with you, right? They need to know that what you do is you do competently, do it well, and that you're really interested in them, okay? And you're really interested in the science that you're doing. So you need these, right? And again, that goes in the category, right? And you need a fundamental belief in the student's ability, regardless of their background. You see, talent and drive can come from anywhere in the country. And, if you recognize that, and you believe the students have to know that you believe in them. And one thing that I can say, if you believe in yourself, if you think that you can make a significant difference in the trajectory of the life of your student, that's enough to keep you going. That's enough for you to go the extra mile and do what you can for that student. I have never had to choose between involving students from less privileged backgrounds and doing the best science I can do. That's never, this is not an either or. Okay, never happened to me. I can't remember a single case where that was true, because people don't believe that. A lot of the people said, "Oh, come on, you're shot." No, never happened. Once a student entrusts you with their future, they'll stay up. They'll work weekends. You'll get. They'll do their part. Make them part of your community. When you go to a conference, bring them along. Introduce them to your colleagues. This last part I say, do well by doing right. Okay. I don't think that I may not be the most altruistic person in the world, but having had this record has been good for me personally. Okay, in two ways. First of all, on a kind of selfish grounds, the funding agencies like it. People recognize that. The university likes it. But the most important thing I think at the end of the day is I feel better about what I've done. Right. For all you mentors out there, the most fulfilling and satisfying thing you can do is move a student along that might not have had that trajectory so long for you. Okay, that to me, that's what makes it all worthwhile. I don't fly business class. I fly sardine coach class, sardine can coach class like everyone else. Not like my guys I went to college with who were like work for banks and stuff like that. I don't care. I mean, to me, I think most people professionally, I'm going to say this to the younger people as well. If you want to get a job, that's really great. You want to do something that's going to help the world. You want to do something. If you want to feel that personal fulfillment, you want to do something that's going to help people's lives for the better. Okay, whether you're a doctor or whatever, if you're a professor, this is the kind of stuff you want to do. Because at the end of the day, this is what really helps you sleep at night. And I think, oh yeah, that's it. Thanks very much. I'd be happy to answer questions.
All right, are there any questions in the audience?
So you mentioned earlier that not a lot of people are using the FFC, correct, in the country. Is
Right.
there a reason for that other than cost, or is it just?
It's That's not an added, the cost is not the reason, because these instruments are less than $500,000, and people are buying new NMRs for way more than that. I think there's just, people don't know about it as much, right? That's probably the main reason. And most of the, when I go to conferences and I show results, people go, oh, that's really nice, you can do that. But there isn't that much knowledge about it, at least not in the US.
Yeah, so you mentioned some of the electrolyte materials for solid state batteries. Are there some elements which are favored more for making animals impacted?
Okay, so let me see if I can dissect it, but financially correctly or heard correctly. The solid electrolytes, what's the connection with cathodes and anodes?
Yeah, so you mentioned about the electrolytes, right? Now,
Right.
for making the anodes and cathodes, are there certain elements which are favored?
Yeah, well, the idea is that, the advantage of a solid is that you don't have to use the same composition for the entire battery. A liquid electrolyte is, of course, you have it from the separator itself. It also soaks through both electrode particles. And it's the same, and if you could somehow tailor the composition to be more stable on the anodic side and cathodic side, you have that advantage with the solid, you do not have the liquid. That was the point I was trying to make.
So you mentioned, in like the first topic, that usually when you talk with companies and the price of water and the features and
Right.
are you calculating, when you said that the water was stable, is there something you're calculating, or is it as simple as just saying our device doesn't
Good question.
stop working?
Yeah, well, that's the first thing. It doesn't, the battery doesn't start smoking.
Sure.
But actually, what I haven't shown, and we've done a lot more on, what I have not shown is that we've actually been able to tear apart the cell and look at the NMR and find roughly the same water content. Yeah, after a couple of cycles.
So kind of in that same line of question with the water, sorry, I didn't mention this. Are you trying to use that copper cellulose in a lithium ion battery?
Yes, well, but we could use the lithium, we're actually, for RPE, they want us to make a lithium metal battery. Right?
So if there's any residual water, is that concerned or like?
It's apparently not. I mean, that's the first question, that's the first question people ask. But apparently whatever the residual water is in it does not react. Maybe after 1,000 cycles it might. But yeah, it doesn't, it's only a few percent. Okay, so, apparently it doesn't react with the metallic lithium.
Something for the NMR, are you searching for that, or is it completely wasted?
Oh, well, nominally, NMR is nominally a non-destructive technique, but, you'd have, you'd have to kind of smooth it out again, but you don't do any chemical analysis. You don't add stuff to it unless you're doing solution NMR, you dissolve it, okay, but, in the solid state NMR experiment, we just, pack it in the rotor and do the experiment. There is a caveat to that. A lot of these materials are air sensitive, so we have to use hermetically sealed rotors for that. And then we could use a sample for another technique.
So I understood how adding the DP technique, like, to altering the H donors, H acceptors, but I kind of missed how that relates to like better electrolyte performance.
It's a very good question. Okay, so you want, if you lower the viscosity and you don't sacrifice the ion concentration, then you get a better performing electrolyte. That's essentially what you're doing with lowering the viscosity. And you break up the
Can you tell me about your most challenging student without saying their name? What made them challenging?
Are they in the room?
How did you do it?
Oh, I've had challenges, but I've had students that just dropped out. Okay, and I haven't heard them. Sometimes I wonder what happens, right? There's only so much you can do when you have situations that and it hurts me. Sometimes I take it a little too personally, and that happens. But, a couple of times it's happened when that's the worst thing I've experienced when students have experienced. But
Yeah, I had a question about the fuel cell batteries.
Uh-huh.
Do you generally, does that spend, does it get mixed back in the big tank, or do you have like a separate tank for spend?
You have, we have two separate tanks, and the flows are separate, you have pumps on each side. And what happens at the electrode surface, you have your electrochemical redox, and you basically have the, redox reactions, and the tank on one side gets depleted with that particular oxidation state, let's say radium, and the other one gets depleted in its oxidation state, and that's when you recharge. Okay, but the electrolyte streams are separate.
Is there, on top of that, like, do they're both, you can't be counted for, you have to be concurrent flow with that, or?
I'm sorry?
Can you, is it like, they're both depleted, so do you have to do a concurrent flow, or can you do a counter flow?
No, it's concurrent.
Okay.
Yeah, I'm not an expert on flow batteries, but, I don't know if it's 1-to-1 or whatever, but it's concurrent.
Thanks.
For when you're measuring the diffusion coefficient, are there no other methods, analytical tools to use other than NMR? Like why NMR?
Okay, one of the best ways to measure diffusion coefficients is radio tracer diffusion. And traditionally, you have to have a radioactive isotope. Let's say if it's sodium, let's say you do sodium 22, for example, and you basically prepare your sample and you heat it up or whatever, and you section it and you measure the radioactivity in each section. It's enormously complicated. There are very few places in the world that can do that because they don't have isotope facilities, right? But that's a great way to do it. Very few places actually do it. And you also have to have an appropriate isotope of the ion that you want to measure, and that's not so easy to do. Okay, there are electrochemical methods where you have a voltage pulse and then you look at the relaxation. Those are very indirect and highly subject to interpretation. NMR is the best way.
The technical data diagram is shown. In practice, when you are working with the practice, do these subsequent fields individual participants when like exposed to different conditions?
Sorry, one more time.
With the data diagram you showed about. Like,
Oh, for the techniques, yes.
Yeah. Other situations where based on the environment, you degrade into their individual components. And
Yeah, the technique point can change a little bit with temperature, for example. Can change a little bit.
And does it make the advantage run into challenges or any difficult?
Well, fortunately, there's a lot of literature out there, so that can give us some guidance for things that might work. And then we try them and some of them work.
May I ask you, how do you choose when and where you go back?
I didn't choose it, but that's the one that's most successful. But I think that if you want to make if you want to really go to renewable energy on a large scale, like 40% of our energy budgets, it's probably too expensive at this point. But that's the one that really works and that's out there.
I know a lot in our rhythm part of Dr. Brothers polymer like as well. We do a lot of mechanical testing because that's also used for the polymer. Like so going back to the Cilios, selling folks each ones, do you do mechanical testing on those?
But our colleagues do. Okay, we measure things like moduli, stuff like that. And this stuff looks like it looks like when it comes off, it looks like paper, right? A piece of paper.
Yeah.
And they seem to be mechanically robust. And my colleagues do some of that mechanical stuff.
What sort of
There's a technique called DNA, dynamic mechanical analysis, and for example, they'll measure the elasticity, they'll measure the bulk modulus. I'm not involved in any of those measurements, but I know that's something that the agencies want to see. They want to know how this stuff is going to hold up. Not just when you make the battery, but when you have large scale, when you're making batteries commercially, you have these huge machines and huge colors, and how these things are going to come off the roll. Right, so that's a very important aspect of it, which personally I'm not involved in.
Question about the school upgrade, how efficient is the energy storage?
The round trip efficiency is typically better than 85%. Okay, that's the commercial ones. Have time for maybe one more question?
Going back to those on a separate topic, so you said the lithium ions are more mobile than the TFSI ion.
In this material, yes.
So have you ever done any alterations to the anion? Maybe, I guess part of my question is, do you think TFSI in some way might inhibit the flow of the cations then? Or is there some way to tweak the anion structure to allow for the cation to flow better?
Well, we think the cation is flowing well enough. The only reason to go with something else besides PFSI, there are other reasons, right? For example, maybe you don't want chlorine in your battery, okay? Or you want to find a lower level salt, something like that. But in terms of transport properties, the TFSI is just fine. FSI is also good. FSI might be a little better. Any last one?
That 3 terawatt square that was over Arizona, how big do you think that would get if you put it in like Canada?
Yeah, also realistically, of course, you know, solar energy collection would be distributed, but it's just to show that it's possible. All right, let's take our speaker one more time.
All right, you want to play for that? I have a class. Well, that's not my problem.
Or I'll send Bertrand the same bill I showed you. I showed the Dr. document today. He almost gave it to you. I just gotta do a little more photoshopping, so it applies to me.
Yeah, that's
So.